Okay, so today and in our previous lessons, we've been looking at titrations, and with that comes some calculations that we need to look at. So how do we actually know when that reaction is complete? So in our burette, we have got either an acid or a base of known concentration, and we will be able to determine how much volume has been used of that solution. In our conical flask, we have a solution with an unknown concentration, but we know the volume that we've put in there. So using this information, we can actually calculate the concentration of that unknown solution. So we need to know when the equivalence point is, and this equivalence point is determined from our reaction or from our titration curves, which we will look at a bit later. But if we know the reaction between the acid and the base, we can use the mole ratio to actually work out that concentration. So let's have a go at a couple of questions, and that should make things a little bit clearer. So there's a couple of steps we want to follow when we want to calculate this unknown, and it was made very clear in the Pearson textbook. So the first step we're going to do is write a balanced equation. From that, then, we're going to use the information from our experiment to determine the volume of the average titer. So it's a titration. So titer is coming from that word, and that is the average of the 3 or 4 runs through and measuring from that burette. You're then going to use the concentration of the standard solution, the one that you know the concentration of, to calculate that volume there. So you're going to use the concentration of the standard solute to calculate the amount in moles. So this is the mole ratio we're talking about. Now, using that mole ratio, we're going to look at the equation again, and therefore we'll be able to see how many moles of the unknown should have reacted in that titration. And again, using this combined with the volume that we already know that was in the conical flask, we can determine the unknown concentration. So let's have a go at a couple of practical examples. So here, we've got the concentration of hydrochloric acid was determined by titration with a standard solution of sodium hydroxide. Now, we are putting 25 mils of HCl into our conical flask, and it was titrated with, so it was reacted with a 1 molar solution of sodium hydroxide, and the titers, which is our amount that was used in the titration, was 25.05, 22.10, 22.05 and 22 mils was required to meet the endpoint. So this one here is obviously our rough draft, our run through. And you can see that it is quite different to the other 3 amounts, so we're not going to include that in our calculation. So the question's asking, what is the concentration of the HCl acid? So let's start with following those steps and write a balanced chemical equation. So we're starting with HCl, aqueous, reacting with sodium hydroxide, also an aqueous solution, forming NaCl, which again, using our solubility rules, we know that that's aqueous as well, plus our water, which is a liquid. Now, if we have a look at this and try and balance it, we can see that it's already balanced. So we can see again here that it's a 1-to-1 ratio, producing our 1 mole of water. So we need to discard that rough titer or any that's not concordant, and what that means is not any that's kind of within a 0.1 mil range, so it's an outlier. So that one has gone. So our second step now is calculate or determine the volume of the average titer. So we're now going to have to work out our average titer. So we've got 22.10 plus 22.05 plus 22 and divided by 3. So if we do that calculation, we work it out to be 22.05 mils. Now we're going to use our concentration formula and rearrange it in the form of moles is equal to concentration times volume. So again, similar to what Col has used before, put our name on our CV. Helps us remember that formula. So we've got the concentration. We already know what that is. It's 1.00. Remembering to use the number of significant figures in the question, times by our average titer. So if we convert this into litres, it will be 0.02205 moles. So our answer is going to be the same, 0.02205 moles. So we now know the moles of sodium hydroxide. Now we know the mole ratio is a 1-to-1 ratio. Therefore, we can say the moles of HCl is equal to the moles of our NaOH. So with that, we can say that the moles of HCl is also equal to the 0.02205. As you can see, I'm having issues with this screen. So knowing now that the moles of HCl is the same as the moles of NaOH, we can now calculate the concentration of our HCl. So our concentration of HCl is equal to N over V. We know the moles. We know the moles, which is 0.02205, and we know the average. We know the volume that we had in our solution, which was 25 mils. So when we do that, we get 0.882 moles per litre. I'll fix those 8s up because I know you'll hate them. Moles per litre, and that's our concentration of HCl. Let's flip to the next screen now, and I'll give you a go at doing that, and we'll pause the video and compare your answers with mine. Have a go. So how did you go with that one? Having a look at this question now, the concentration of a solution of barium hydroxide was determined by titration with a standard solution of hydrochloric acid. So we've got 10 mils of barium hydroxide was titrated with a 0.125 molar solution of HCl. Now the amount of HCl required was 17.23, 17.28 and 17.21. So we've got the concentration of HCl and we've got the volume of HCl. So from that we can calculate the moles of HCl that we used. So again, first of all we write our equation and it's there on the board. We can calculate the moles of HCl used by using the molarity that was given and the average titer, and we get 0.002155 moles. So looking at the initial equation, we've got the mole ratio there of 2-to-1. So 2 moles of HCl for every 1 mole of barium hydroxide. So given that's the case, we're going to need to halve the amount of moles of NCl to work out how much of barium hydroxide we're going to need, and our answers there down the bottom. So now we've got to calculate the concentration of barium hydroxide, so that is our moles over our volume. We've just calculated our moles, and our volume was a 25, no it wasn't, it was a 10 mil volume. So we need to change that one there to 0.10, and of course that's then going to change our equation. So hopefully you didn't fall for the similar example that we just had there. So 0.0010 0.0775 divided by 0.10 equals a concentration of 0.010775. Now looking at the number of significant figures we've got, the smallest number is our 0.125 molarity. So we're going to round off here and we should get our 0.011 moles per litre. So let's look at another example now, and that's one that involves a dilution. So we've done a fair bit of dilution over the last 18 months, or 12 months at least. Here we've got a commercial concrete cleaner, contains hydrochloric acid. We're taking out 25 mils of that cleaner and diluting it to 250. So the first thing we're needing to look at is, well, what is our dilution factor? So our dilution factor here is our 25 mils, so I'm 250 down to a 25 mil in that solution. So it's a 10 times dilution there, or a 1 in 10. And from that we're taking 20 mils of sodium carbonate. And we know that molarity. So the first thing we need to do is write that equation. So we are reacting HCl, which is aqueous, with our sodium carbonate, also aqueous. And it's producing, hopefully you remember, NaCl, also aqueous, water, and some carbon dioxide gas, water being a liquid. So now the first thing that we've got to do here is calculate the number of moles of sodium carbonate. So our moles of Na2CO3 is equal to the concentration is 0.4480, so 0.4480, and the volume is 20 mils in that one, so it's 0.020. So with that we get 0.008960 moles. Now we haven't yet balanced that equation up there. So we've got HCl, NaCl, we've got two NAs there, so I need two NAs there. That'll make two over there, and we should now be good. So you can see that then the moles of Na2CO3 is equal to half the moles of NaCl. So rather, if I've got that quantity of Na2CO3, I'm going to have two lots of the amount of HCl. So the ratio there is a 1 to 2 for NaHCl. So we've worked out the number of moles that we require, and from the question you can see that 19.84 mils of the cleaner had been added into the reaction vessel, and so that's our volume that we're going to use to find the concentration of HCl. So we know the number of moles and we know the number of mils that we used. We convert that to litres, and we'll work out the diluted concentration of HCl as being 0.9032. But of course we've got that dilution factor that we calculated before, and it was a 10 times dilution, so we need to times it by 10. And so our final concentration, or rather the initial concentration prior to dilution, but our final calculation is that it's 9.032 moles per litre. Again, looking at four significant figures as we've been given in the question.